Today we're going to talk about photoelectron spectroscopy. Photoelectron spectroscopy, also called PES, is a technique we can use to measure the relative energies of electrons in atoms and molecules. This is used for several different things. We can use it to understand the bonding or the composition of an atom or molecule, but we are going to use it to help us better understand atomic structure, especially electron structure. We can use it to explore concepts like electron shells, subshells, electron configurations, and much more. I want to point out that PES is not the same thing as mass spectrometry, even though it generates a spectrum that can look a little similar to it. So don't get these confused on the AP exam. Remember, mass spectrometry is what we use to measure the relative abundance of isotopes. But in photoelectron spectroscopy, we're looking at relative numbers of electrons and binding energy, and we'll get to this in just a moment. Let's talk about how PES works. First, a sample of what you're trying to analyze is bombarded with high-energy radiation, such as X-rays. This causes electrons to be ejected from the sample. The electrons travel to an analyzer where their kinetic energies are recorded. They then go to a detector, which counts the number of electrons at various kinetic energies. One of the terms you need to be familiar with as we look at photoelectron spectroscopy is binding energy. The binding energy is the energy required to move or eject an electron. If you take a look at this photoelectron spectrum, you will see that binding energy is on the x-axis, and you'll see how this works in a moment. Now, binding energy is different from ionization energy, which we study as part of periodic trends. Ionization energy is the energy required to remove the most loosely bound electron, but binding energy can be for any electron. When you're working with PES problems, there are three important things to think about. The first is the number of protons in the nucleus. The second is the amount of shielding that happens because of other electrons. And the third is the distance the electrons are from the nucleus. Now, this is an example of a PES spectrum. On the y-axis, we have the relative number of electrons, and on the x-axis, we have the binding energy, which is measured in millijoules per mole. You will notice that this scale is a logarithmic scale where everything increases by a multiple of 10. One thing that's very important to remember is that this is backwards compared to what we're usually used to looking at. The higher energy is plotted on the left-hand side, and the lower energy is on the right-hand side. Higher numbers are on the left, lower numbers are on the right. This is very different from when we did mass spectrometry. One way that you can help yourself remember this is to picture the proton on the left-hand side of the screen, because ionization energies are higher for electrons that are very close to the proton. This is an example of a typical PES spectrum. It has peaks, and these peaks are at different binding energies. Remember, the higher binding energies are on the left, and they're closer to the nucleus. And the lower binding energies are on the right-hand side. Each peak represents a different orbital or group of orbitals, and the orbitals of a particular shell or energy level are clustered together. In this example, you can see that the 2s and the 2p are really very close together. They're even closer together than they look because this is a logarithmic scale. The height of each peak shows how many electrons are in the orbital. In the example on the left, there are 2 electrons in the 1s orbital. We have 2 electrons in the 2s orbital, and then we have 4 in the 2p orbital. Now let's take a look at the binding energies. Notice that the numbers on the x-axis move from high to low, zeros on the right, This means the farther to the right you go, the lower the binding energy is and the easier it is to pull off an electron. The closer the electrons are to the nucleus, the harder they are to remove, and this makes sense if you remember Coulomb's law. In this example, you can see that the 1s electrons have a binding energy of 80 megajoules per mole. This is how much energy you need to put in to remove a 1s electron. But if we look towards the right, we can see that the 2s and the 2p electrons have much lower binding energies. You only have to put in 2 megajoules per mole to remove a 2p electron. And this makes sense when you consider the fact that 2p electrons are farther from the nucleus than 1s electrons are. Now let's take a look at a couple examples. We're going to start with the spectrum of lithium, which has an electron configuration 1s2, 2s1. As we look at this spectrogram, we can see that we have two peaks. One of them is for the 1s subshell and the other is for the 2s. Remember that when we're talking about binding energy, the higher values are going to be to the left and the lower values are going to be to the right. We see that in our 1s peak we have 2 electrons, and in our 2s peak we only have 1 electron. So the 1s are closer to the nucleus and those take more energy to remove. And we can see that because that peak is on the higher binding energy side of this particular diagram. Now let's go through some spectra. I'm going to use these wonderful slides from chemibear.com. Now the first one is the spectrum for hydrogen. If we take a look at this, we'll notice that we only have one peak, and this will be for the 1s orbital. And when we look at the number of electrons, we see that we only have 1. And we know that the electron configuration for this atom is 1s1. Now let's take a look at a helium atom. We have one peak and it represents the 1s orbital. And when we look at our y-axis, we can see that we have 2 electrons. The electron configuration for helium is 1s2, and this is what we see reflected in the spectrum. We've already taken a look at lithium. We have 2 electrons in the 1s orbital and 1 electron in the 2s orbital. And just to make it clear that we are dealing with 2 different shells, we'll put the first shell on the left and the second shell on the right. These will be useful in a bit when we start making comparisons. Now we'll go to the next atom in line. It's beryllium. And we have 2 electrons in the 1s orbital and 2 electrons in the 2s orbital. Once again, I'm going to draw a line between our 2 shells, n equals 1 and n equals 2. And you'll see why I'm doing this in a moment. Our next atom is boron, and we have 3 peaks here. We have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and we are adding 2p orbitals. We only have 1 electron here. I'm going to split these into shell n equals 1 and n equals 2. On to carbon. Once again, we have 3 peaks. 2 electrons in the 1s, 2 electrons in the 2s, and 2 electrons in the 2p orbitals. And we will draw a line to show that we have 2 different shells. Now let's look at nitrogen. We have 2 electrons in the 1s orbital. We have 2 electrons in the 2s orbital. And we have 3 electrons in the 2p orbitals. Our next one is oxygen. We have 2 electrons in the 1s, 2 electrons in the 2s, and we have 4 electrons in the 2p orbitals. We still only have 2 shells, and our valence electrons are in the second shell. We will add another proton and electron, and we have fluorine. We have 2 electrons in the 1s, 2 electrons in the 2s, and 5 electrons in the 2p orbitals. On to neon. We now have an extra electron and it has gone into the 2p orbital. Our electron configuration is 1s2, 2s2, 2p6, and we have a full second shell. Now let's go to the next row. We have sodium. We have 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, and we are adding one more orbital. This will be the 3s. And I'm going to draw these lines again so that you can see now we have 3 different shells. Shells number 1 and 2 are full, and our valence electrons are in n equals 3. Now I'm going to skip over to calcium right now, and we can see we have 4 different sets of peaks. There are 6 peaks in total, and we have electrons in 4 different shells. Notice how the binding energies for the 2s and the 2p are really close together. They're within 10 megajoules of each other. Also notice how the binding energies of the 3s and 3p are very close together, within about 2 megajoules of each other. Also remember that the scale on the x-axis is logarithmic, so the binding energies of the 1s electrons are about 660 times higher than those of the 4s electrons. But the key point is that for any given shell, the ionization energies of the subshells are actually very, very similar. I'm going to show you these slides again, and I'm going to show you a couple others, but I'm going to show them to you in a different way. I want you to look for some patterns. Here is the spectrum for hydrogen again. On the left-hand side of the graph, I've put a little red dot with a plus in it. This is supposed to represent a proton. Now I'm going to go through these atoms one by one. Take a look at the binding energies of the 1s and the 2s and the 2p. What happens to these binding energies as I add protons? You should be able to see that every proton I add shifts the binding energies to the left. Remember, as you go across the row of a periodic table, the first ionization energy, which is the ionization energy of the valence electron that's easiest to remove, gets larger and larger. And just to clarify, I'm not talking about the peak getting taller, I'm talking about it shifting towards the higher end. Ionization energy gets larger as you go from the right to the left. And you can see this as we speed through this second row of the periodic table. See how that P2 peak is shifting over to the left with every additional proton we add. But when we get to sodium, we enter another shell. Now we have a 3s peak, and that has a much lower ionization energy than any of the other electrons in the spectrum. And the reason has to do with Coulomb's law and the fact that this electron is farther from the nucleus than the electrons in the second shell, which is right below it. As we continue across the third row of the periodic table and add more protons, we see a similar phenomenon. The ionization energies keep getting larger and larger as these peaks shift to the left. And this continues until we get to potassium, and we add the fourth shell. You see, we now have an electron with a binding energy that's much lower than any of the others. It's really easy to pull this electron off, and the reason is because it's farther away from the nucleus than any of the other electrons in this atom. One other thing I want you to notice as we go through it, it's not just the last electron that is affected by the addition of all these protons. The binding energies of all the orbitals, no matter where they are, shifts to the left as you add more protons. These electrons feel more and more attraction to that nucleus. And this is related to Coulomb's law. Increasing the charge increases the attractive force. These electrons also get pulled in closer to the nucleus, and because of this, the radius of the atom decreases. These atoms get smaller until you add another shell and move to the next row of the periodic table. Now let's do some practice problems. The first type of practice problem is really very easy. We should have looked through enough of these by now that you could take a look at this particular spectrum and figure out which element this is. Pause the video and give it a try. Okay, so we see we have one peak, that is a 1s, and we can assume that each of these horizontal lines represents one electron, so we have 2 electrons in the 1s orbital. That gives us an electron configuration of 1s2, which is the electron configuration for helium. That is our element. Now let's try another one. We have 5 peaks here. We can go ahead and label them from left to right and start writing an electron configuration at the top. So we'll start with the 1s, and we have 2 electrons. Then we'll go to the 2s, and we have 2 electrons. Then we'll go to the 2p. We have 6 electrons in this orbital. Now we'll move over to the 3s, where we have 2 electrons, and the 3p, where we have 3 electrons. And we've been writing our electron configuration as we go. And we can count up the electrons in this electron configuration. And we have 15 electrons, and we are assuming that this is a neutral atom. So if we look at our periodic table, 15 electrons in a neutral atom would mean 15 protons, and that's the atomic number for phosphorus. So phosphorus is our element. Now let's get to the fun stuff. In this particular spectrum, looks like we have 2 spectrums that have been superimposed on each other and are in slightly different colors. We're told that one of them is boron, and we're told that one of them is fluorine, and we have to figure out which one is which. Pause the video, take a moment, see if you can figure this one out. Now these peaks aren't labeled, so I'm going to have to go to the periodic table and figure out how many electrons I should have for boron and how many for fluorine. And I find that boron has 5 electrons and fluorine has 7 electrons. I'm assuming these are neutral atoms, so they have the same number of electrons as their atomic number. Since there are more electrons in the pink peaks than there are in the blue peaks, I am going to assume that the pink peaks represent the fluorine and the blue ones the boron. Next question, why is the one peak in fluorine so much taller than the others? Well, why don't I go ahead and label my peaks and count the electrons? And I'll do this for boron, and I'll do this for fluorine, and I see that fluorine has a lot more p electrons, and working backwards from the fact that I know I have 7 electrons, I can do a little math and figure out that there must be 5 electrons in that 2p suborbital. So the peak is higher because fluorine has more electrons in the 2p orbital than boron does. Now the next question is, why is the first ionization energy higher in fluorine than it is in boron? Now the ionization energy is the energy that is needed to pull off the valence electron that's easiest to pull off. And we can tell which one this is because they should have the lowest binding energy. So they will be the electrons farthest to the right. And we can definitely see that the first ionization energy for fluorine is going to be higher than it is for boron. Indeed, we see that the whole spectrum for fluorine is shifted to the left. Pause the video and see if you can figure this one out. The answer to this question has to do with the number of protons. Boron only has 5 protons, but fluorine has 7. Adding more protons results in a greater positive charge on the nucleus. And if you have a greater positive charge on the nucleus, you're going to have a greater Z effective. That means the electrons are going to feel more of a positive force. These electrons are being held in tighter. It is more difficult to remove them. And that's why it's harder to remove an electron from a fluorine atom than it is from a boron atom. Now the next question is, which atom is smaller and why? Pause the video, see if you can figure this one out. Okay, so the reason for this, it's similar. As we add more protons to fluorine, the Coulombic force gets much stronger. These pull the electrons closer and closer and closer to the nucleus, so the atomic radius gets smaller. Fluorine has more protons, so there's more of this pulling in effect than you see for boron. We also know that atomic size decreases as you go from left to right in a row of the periodic table. And fluorine is to the right of boron. Here's another question. Why is the s orbital closer to the nucleus in fluorine? Well, it's the same reason. We have 2 more protons. The attractive force is greater. The electrons in all of fluorine's orbitals get pulled closer to the nucleus. Okay, here's another fun question. This is the spectrum for sulfur. Which peak shows the first ionization energy? Well, the peak that shows the first ionization energy is going to be the one with the lowest binding energy, and it will be this peak here. Low binding energy means low ionization energy. Now for the fun one. This is the spectrum for sulfur. We are asked to draw the approximate location for the peaks of aluminum. Pause the video and give it a try. Well, the first thing I want to do is put together the electron configurations for sulfur and aluminum. And I can look at the periodic table to help me do this. And I recognize that one of the main differences is that aluminum has only 1 electron in the 3p subshell, and sulfur has 4 electrons. So I'll be able to draw almost all the peaks the same size, except for that 3p peak, which is going to have to be about 1/4 the size. If I look at the periodic table, I also see that the atomic number for aluminum is 13, and the atomic number for sulfur is 16. Sulfur is going to have more protons than aluminum, and this means my spectrum is going to be shifted to the right, because the electrons in aluminum aren't going to be pulled in towards the nucleus as much as they are for sulfur. So when I draw this, I shift everything to the right, and I make my 3p peak about 1/4 the size of the 3p peak for sulfur, which is going to be half the size of one of my s peaks. Here's one more problem, and this one's kind of interesting because they've only given us the 2p electrons. They haven't given us the entire spectrum. So we have the 2p electrons for N and the 2p electrons for S. They want to know which of the following best explains the difference in signal intensity of the 2 peaks. And for us, that's going to translate into peak height. Now let's think about this for a minute. Let's look at the first one. Nitrogen has fewer 2p electrons than sulfur has. And I could write out my electron configurations or just take a look at the periodic table and notice that nitrogen has 3 2p electrons. And since sulfur is in the 3rd row, all of the p orbitals in its second shell should be filled. That would be 6 electrons. So this could definitely explain our peak. Let's go through the rest of them and just make sure. Nitrogen has fewer protons in its nucleus than sulfur does. Well, that's definitely true too, but the fewer protons, that's not going to affect our peak, but it might affect how much the 2p peak is shifted to the left, since the binding energy would be higher with more positive charge. And we actually do see this in the graph. Sulfur has more electron subshells than nitrogen has. Yeah, that's true too, but it's not going to affect our peak height because we're only looking at 2p. And the last one, sulfur has more electrons in its valence shell than nitrogen has. Well, that's true too, but it's not going to affect the intensity of that 2p spike. So our answer has to be A. You should now know what a photoelectron spectrum is, how to read a photoelectron spectrum, and how PES can help us understand periodic trends.